Hi everybody, welcome to Mrs. John's class. This is for year 12 Atomic and Nuclear Physics, and this is a continuation of the first lesson. I'm elaborating now on Rutherford's model of the atom. So the two things that you need to know prior to Rutherford, I did give you a brief history in my previous video, but you need to know about Dalton's model, who said that the atom was indestructible and it was very small. And then you also need to know about Thompson's model of the atom. Thompson's the one who discovered the electrons, and he said that the electrons were embedded in a sphere of positive charge and the atom was electrically neutral. Now, both Dalton's and Thompson's model did have their shortcomings, and Dalton's model could not explain why electrons were given out from the atom, why the atom was no longer the smallest part of matter, and Thompson's model could not explain why, when atoms are heated, they give out color. They give out light, and light is of a particular color. And he also could not explain why atoms show group similarities, which led to the discovery of the periodic table. Now, at the time of Rutherford, now as you know, Rutherford was a New Zealander, but he did all these experiments in the UK. He did live in the States, and he did live in the British Isles in the UK, and he worked not on his own. He actually worked with Geiger and Marsden. He actually supervised the experiments. And the thing is, the atom is so small we can't see it with our naked eye. But even though we can't see it, we do know a lot about the atom. And a lot of our knowledge about the atom actually comes from firing alpha particles at the atom. Okay, and so what was known when Rutherford was doing his experiment was that they knew that the atom was electrically neutral. It was known that electrons can be given off from the atom. They also knew that atoms show group similarities, which led to the discovery of the periodic table. So a few things were already known. And what Rutherford was trying to do was that he was trying to study the structure of gold atoms. He wanted to know, like, what's inside the gold atoms, what makes it up. So what Rutherford did was, it's called his scattering experiment, and I'm just going to draw a diagram of what his experiment looked like. He did lots and lots of experiments. He's credited to having discovered and be the first one to do a lot of things. One of the things he did was he experimented firing alpha particles at a thin gold foil. So what he took was, there was a chamber, and in this chamber he took all the air out. So when you take all the air out, you have what's essentially a vacuum, and where there is a vacuum you call it an evacuated chamber. So he did not want the alpha particles to encounter with anything else but the gold foil. Now, how is he going to get the alpha particles? So for that he used a radioactive source. Now you will learn about radioactivity, and these are unstable elements that spontaneously give out radiations, and one of the type of radiation is the alpha particle. Okay, so he had a source of radioactive material, and he used radium for this because radium gives out alpha particle. And there was actually a collimator. So that is a narrow opening through which these radiations could go out from the radium, a radioactive source. So these were alpha, this was a source of alpha particles. And then he had this very thin gold foil. Now the gold foil was only a few millimeters thick. It was only, a foil is a very, very thin piece. You know what an aluminium foil looks like, and gold can be beaten into very thin sheets. And it's only a few atoms thick. And the reason for this is he was thinking that the atoms are going to pass through the gold foil. And in order to know what happened to the alpha particles, he wanted to know what happens when they come to the other side of the gold foil, because they're so tiny and you can't actually see them. He had this coated with zinc sulfide. So when alpha particles strike the zinc sulfide anywhere on the screen, it's going to scintillate, okay? And then he had some sort of a device where he could actually count number of alpha particles that was hitting the screen at the back. And what did he find? So you need to, when you're learning this, you need to know what his observations were. What did he see? What that was the evidence because he saw it. What was the reasoning and what was his conclusion? So it's under 3 headings, okay, that you need to learn this. What he saw, that's the evidence. What he reasoned out and what was his conclusion. So what he saw was that most of the alpha particles went straight through. So they went undeflected, most of them, majority of them. So he saw all these spots over there. So because most of the alpha particles went straight through, his conclusion was that most of the gold atom is empty space. That was his first conclusion, okay, because it didn't encounter anything. So most of the atoms went straight through was what he observed, his evidence. His reasoning was if it's gone straight through, then they did not encounter or come across anything in its path. So if it hasn't come across anything in its path, it means most of the atom is empty space. So if most of the atom is empty space, then the matter of the atom is actually concentrated in a very, very tiny space, which he called the nucleus. Now, then he also found that some of the alpha particles, something like 1 in 2000, I think, some of the alpha particles didn't actually go straight through. He found that some of them were deflected. So they struck not straight behind, but there. So that was his evidence. That was he saw that some were deflected. Deflected means not go along the same path, but bend, you know, right or left, up or down. And so his reasoning was alpha particles are helium, essentially helium nuclei. They're made up of 2 protons and 2 neutrons. He knows that alpha particles are positively charged. So when you bring a positive charge near another positive charge, they're going to repel. So he concluded that the matter that makes up most of the atom is positively charged. So he said that the nucleus is positively charged, and the positive charges he gave the name protons. So he said in the nucleus you have positively charged particles called protons, and that is the second conclusion. Then the other thing that he saw is that a very, very few of the particles, like 1 in 8,000, once in a while, you had this sort of thing happening. The alpha particles hit the gold foil and they bounced back. They got reflected. So that's by large angles. So this is going straight through most of them. A few of them veered off a little from their paths. They got deflected, and a very, very few of them actually got reflected. So he saw this. So that was the evidence. Now, if something hits something and it bounces back, and without the gold foil itself budging, there are 2 things that happen. So the gold, the mass of the atom is really, really very large. It's concentrated in the nucleus. So all the mass of, most of the mass of the atom is concentrated in the nucleus. It's much more massive than the alpha particle itself. The nucleus of the gold atom is much more massive than the mass of an alpha particle, and because itself did not budge. But the other thing is, now the nucleus is positive, so there's a positive charge and there's the alpha particle coming towards this positive charge. And so the force of repulsion increases, gets more and more and more as it gets closer. It's so strong that this force of repulsion, that it goes back. So there are 2 ways of looking at it. So the force of repulsion is so great that it bounced straight back. Also, that if it encountered the gold nucleus, it was so massive compared to the mass of the alpha particle. So these are your 3 main observations. Later on, Chadwick discovered the neutrons, and then there was, you know, the nucleus of the atom is not just protons, it's neutrons and protons. Neutrons are neutral. Then the other thing was Rutherford had to come up with a reasoning, an explanation of where are these electrons in the atom. Thompson said they were embedded in the positive sphere. Now what Rutherford said was you have the central nucleus with a lot of empty space around it, and in this empty space, orbiting around the nucleus are your electrons, and the electrons balance. The negative charge of the electrons balances the positive charge, and it's held over there in orbit by this electrostatic force of attraction. Okay, Rutherford's model did have a flaw, and that was none of these models were perfect, and because if the electrons are going around the nucleus, they are undergoing circular motion, and so in other words they're accelerating. So if his theory was correct, then the electron should actually collapse into the nucleus, but this doesn't happen. And there was Niels Bohr, who came after Rutherford. He was actually a student of Rutherford. He came up with his theory about electron levels, saying yes, the electrons are outside the nucleus, but they don't actually go around the nucleus. What they do is they occupy different energy levels outside the nucleus, and they can go from one energy level to another, but that is for another lesson. So that's all for this lesson. Bye for now, and I hope you understood.